Welcome back. We are still in section 3.1, graphing equations. We have just finished plotting ordered pairs, as well as determining if ordered pairs are solutions to an equation. So now we would like to talk about graphing linear and non-linear equations. So the line we were working with, 2x plus y equals -6, is in what we call standard form of a linear equation. That typically looks like ax plus by equals c. Now you'll notice a, b, and c are all capital in this case, which means, let me write that again, ax plus by equals c. A, b, and c are capital in this case, which means they are typically integers. A, b, and c are integers, which means whole numbers. We can't have any decimals or fractions when a, b, and c are integers. And also, something else to note is that a is typically positive. It's not a very helpful form when it comes to graphing, so what we would like to do is we would like to change it into something called slope-intercept form. And you are probably familiar with this form. It looks like y equals ax plus b. Now, we in Math 95, instead of using an a, we typically like to use an m. So let me go ahead and change that to an m. And m and b are anything. They could be decimals, they could be fractions, they could be whole numbers. They don't have the stipulation that a, b, and c did up in standard form. The y and the x correspond to the same two variables between the two forms, though. So in order to get our line into slope-intercept form, first I'm going to copy my equation down. It's a good idea to copy an equation down anytime you want to work with it, even if it's sitting right in front of you. Something about writing it down helps you internalize the problem. It also helps you catch any mistakes you might have made. In order to get y by itself, again, this should be a familiar process, I'm going to subtract 2x from both sides. And so that is going to give me y equals... Now, when I do this, when I subtract on this other side of the equation, you might be tempted to go -6 and -2 would give me a -8, and the x tags along for the ride. We just committed one of the biggest algebra sins there is. We just combined two things that were not like terms. You'll notice my magic eraser pen has wonderfully disappeared for me. The -2x and the 6 are not like terms, so they cannot be added together in combining them numerically. So what instead I'm going to do is I'm just going to write it down, -2x minus 6. Here's my mx, here's my b. This is called a linear equation, as is the standard form. These are both linear equations. Other types of equations you might encounter. This first one with the y equals and the big bars and the x minus 2, this is called an absolute value equation. You will deal more with absolute values in Math 111. You may have seen them in our Math 60 class. We are barely going to touch on them. In fact, in your homework you'll see there's number 33. It has an absolute value and I don't want you to deal with it. Putting them in your calculator gets difficult and I don't have the time to cover what you do with an absolute value, so we are going to skip that problem. The second equation, y equals x squared plus 2x minus 3, this should also feel familiar to you. You've spent a little bit of time on this. We will be spending a lot of time on this in this class. This is called a quadratic equation. and my U and my A look like the same letter. Let me try that again. Quadratic. Oh goodness, I can't write. Quadratic equation. There we go. And this bottom one you've probably seen, especially if you just came from Math 65. We will spend a little bit of time with this equation. It's called a square root equation. So now let's talk about graphing these equations. If I would like to graph an equation, using a table of values, first I need to get them in a form that's easy to work with. We like to use our slope-intercept form, our y-isolated form. So I am going to rewrite our equation here. We had y equals negative 2x minus 6. I'm going to write that down here. Same equation, I don't need to solve it again. Y equals negative 2x minus 6. And then we are going to pick some x values and figure out what our y values would be. My favorite x values to use are negative 1, 0, and 1, just because they're easy numbers to work with. You need to have at least one negative value and at least one positive value, and 0 is almost always a good choice. I could choose any other x value that I want. I'm going to pick 2 because I like small numbers. When I get my table of values, what I'm doing is I am plugging my x into my equation for y, just like we did when we were checking to see if things were solutions. So for this first entry, my y value should be negative 2 times negative 1 minus 6. Well, negative 2 times negative 1 is positive 2. If I subtract 6 from that, I get out a negative 4. And you could do this part in your calculator. I'm not going to. I'm just going to talk my way through it. For my second value, if I put a 0 in for x, this whole chunk goes to 0. And I'm just left with that negative 6. For the third value, if I plug a 1 in where my x is, I'm going to get a negative 2 subtract 6. It's going to give me a negative 8. I am actually going to change this x value to a negative 2. Let me just erase that entire entry. I can see that this is just going to continue being negative. I'd like to get some more closer to 0 values for my y value, so I'm going to plug in a negative 2, and I'll just show you what that's going to look like. Negative 2 times negative 2 minus 6. And negative 2 times negative 2 is a positive 4. Subtract 6 gives me a negative 2. So now, I want to put these on my graph. And before I can do that, I need to make certain that I am labeling my graph and putting a scale on it. We need to do that every single time we see a graph in this class. 99.9% of the time we see a graph in this class. So I'm going to put a y and an x because those are the two variables we were given. And then I need to figure out my scale. And the smallest value, the farthest I get away from 0 is a negative 8. I don't get any farther away from 0. So I need to make sure I at least go out to 8. And if I count these, I will find that I go out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I allow this value to be 8, each of these is worth 1. I mentioned before that I like to label my 2's because they are easy to see. And again, I like a square graph, so I am going to just let both of my axes count by 1's. Actually, we'll let our y's count by 1's. I've changed my mind. My x's only go out to 2. So I could really mess with the scale on this graph, and I'm going to put 2, 3, 4. There's going to be one value, 1, 2, 3, 4. I'm going to put my 2 all the way out here for x. So notice that my y scale and my x scale have changed drastically. And I'm allowed to do that. I can pick whatever scale I would like to. So now I'm going to plot my points. First one is when x is -1. Let me make sure I make a note to myself where that is. 1, 2, 3. Those are my 2 x values that I'm going to look at. When x is -1 and my y value is -4. 1, 2, 3. When my x value is 0, my y value is -6. When my x value is 1, my y value is -8. And my next x value, remember, was -2. So I'm going to come all the way here to -2, and I will be down at -2. Now, a nice feature on the smartboard is that I can grab a line and ask my line to go through my points. And so I can start here and make it go all the way through, and I get a nice linear equation. Now, I would like to make this one continue all the way up here. Oh, are you going to get bigger for me, please? There you go. And there's a reason I'm doing this. I would like to figure out what this point is right here. I know my axes aren't quite long enough, and that's not a problem. We would like to do something called finding x and y intercepts. And so first I'm going to tell you how we do that. To find a y-intercept, we're going to let x be 0 and solve for y. Now, we've already done that. This right here is our y-intercept. I'm going to go ahead and write that down. 0, -6. And that corresponds to this point down here. When x is 0, y is -1, 2, 3, 4, 5, 6. It's just as we expected. Now, to find an x-intercept, very similar, except we will let y equal 0 and solve for x. So when I do that with our equation here, it's actually going to look like, I'll do this in purple. We're going to say 0 equals -2 times x minus 6. I add 6 to both sides. 6 will equal -2x. If I divide by 3, I figure out that x. If I divide by -2, I find that x will be -3. If you look, if I were to project where this x-axis intersects this line, it looks like it's going to happen right at x equals -3. So our x-intercept would be -3 and 0. And that would happen right about there, roughly. We will be interested in graphing things other than lines. And using a table of values, we can graph pretty much anything that can be graphed. That's the nice thing about values, tables of values. In this case, our y value is already isolated. Now, look at this little note down here. If you have non-linear equations, you are going to need at least 5 points to get a feel for what the graph is going to look like. Sometimes you'll need more than that. I still like my 0, my 1, and my -1. I need more values, so I'm going to try a 2 and a -2. And I sketched this so that I would have room to add more values if I need to, depending on what the graph is going to look like. So I'm going to put my x up here and my y here. Again, you can use your calculator to plug in your x values and your y values, and if I can figure out how to do a calculator session on this, I will, to show you where all of the buttons are. I'm sure I could figure that out. But in the meantime, we're going to do this just verbally. So for my first point, if I let x equal negative 2, I'm going to have a negative 2 squared. I don't know why it does that. Plus 2 times negative 2 minus 3. So this is going to be a positive 4. This is going to be a negative 4 minus 3. These two cancel out, and I'm just left with a 3. For the next one, I'm going to do a negative 1 squared plus 2 times negative 1 minus 3. A negative 1 squared gives me a positive 1. This gives me a negative 2 minus 3. So I get a 1 minus 2 minus 3. It gives me a negative 4. Zeros are easy. I'm going to have a 0 here, plus a 0 here, minus 3. That'll give me a negative 3. I could have looked at that here. If I let x equal 0, the only thing that's left is at negative 3. And when I plug my 1 in, I'm going to get a 1 squared plus 2 times 1 minus 3. So I wind up with a 1 plus a 2 minus a 3. That gives me a 0. It should have been a negative 3. I apologize, I didn't write that correctly. And then finally, I am going to plug in a 2. So I get a 2 squared plus a 2 times 2 minus a 3. So I get a 4 plus a 4 minus a 3. That gives me an 8. Now, if you're familiar at all with quadratics, you remember that they sort of mirror themselves. They sort of have this smiley face shape. And I'm seeing some mirroring happening here. So if I allow my x value also to be negative 3, I'm expecting that I get a 0 out for that y, but let's just double check it. So negative 3 squared plus 2 times negative 3 should, and I have that subtract 3 as well. I'm looking for a 0 here. So I get a positive 9, a negative 6, and a subtract 3. That does in fact equal 0. So my prediction was correct. Now again, on my graph, I am going to need a label and a scale. So here will be my y, here will be my x. And again, my y value goes all the way down to an 8. So I know that my y values are going to need to count by 1. So I'm going to lay in my 2 up there. And for grins, I could put a negative 2 down here, just so I remember that they're the same scale. My x value, I have some freedom. I'm going to let them count. So here's a 1, and here's a 2. Here's a 1, and here's a 2. To plot these, I'm just going to do what I've been doing. So let's take green. Green sounds like fun. I'm going to start with negative 3, 0. I'm going to go negative 2, negative 3, 1, 2, 3. And then negative 1, negative 4, 0, negative 3, 1, 0. And then my 2 should be up at 8. 1, 2, 3, 4, 5, 6, 7, 8. Why did I write 8? I did not mean 8. This plus this minus this gives me a 5. That makes a little bit more sense. And I think I said 5, and I think I wrote 8. So that is not in fact there. That one should go 1, 2, 3, 4, 5. That feels better. Okay. Now, because of the mirroring, I know that my negative 4 should also have a value of 5. He was a little wonky. Let me get him a little bit better there. All right. So now I'm just going to smoothly connect my points. Mostly smoothly connect my points, and there we have a wonderful parabola. A parabola is the name of this graph, and that is a quadratic graph's name. All right, one more slide, and then I'll stop talking to you for this session. I would also like to look at the square root of x minus 1. Again, we can use our calculator to do this. I want to be clever in how I think about this, though. So we're just going to start by picking values of x, and I want to pick nice values for x, and it might take a little bit of thought to figure out what those nice values are. First, I'll try 0. And the reason I did this is because if I plug a 0 in here, I'm going to get the square root of 0 minus 1, which is the square root of negative 1, and that gives us a non-real answer. You might remember that you cannot take the square root of negative 1 to get a real number, so I'm just going to call this not real. Your calculator will tell you error if you do this. Okay, so that wasn't a nice value for x, but it will demonstrate something here. The next thing that I want to do is plug in a 1. So I get the square root of 1 minus 1, which is the square root of 0, which is just 0. If I plug in a 2, I get the square root of 2 minus 1, which is the square root of 1, which is 1. So far, I've just been counting. But what happens if I put in a 3 here? If I plug in a 3, I get the square root of 3 minus 1, which is the square root of 2, which is some ugly decimal number. And I don't know exactly what that decimal is. So square root of 2 isn't my favorite. If I plug in a 4, I'll get the square root of 3. So I don't want to do that. Let's try a 5 next. If I plug in a 5, I get the square root of 5 minus 1, which gives me the square root of 4, which is a 2. That's a very nice value. And so my next x value that I'm going to try is a 10, because the square root of 10 minus 1 is the square root of 9, which is 3, and that gives me a nice value. So occasionally when making a table of values, you sort of have to work yourself backwards, so you get a nice feel for how these work. So again, I need to plot my x and my y. I forgot to label that this was x and this was y. That's helpful. So this is my y-axis, this is my x-axis, and my x goes all the way out to 10. So I need to use this full side here, we'll call that a 2. But my y only needs to go out to 3, so I could let my y's be a little bit trickier. Call that my 2 right there. So now when x is 0, I don't get anything nice. I don't get a value. But when x is 1, I do. When x is 1, I get out a 0. So I'm going to plot my 1 and my 0 there. When x is 2, I get out a 1. When x was 3, I got out a little over 1, which is really hard to graph, so I'm not actually going to plot that point. But when x is 5, 3, 4, 5, I get out a 2, and when x is 10, I get out a 3. And I can graph this function. Now, my x value will never be less than 0, and my y value will never be less than 0. So I have a dot there, meaning my graph can't go past that, and I meant x can't be less than 1. But x can be greater than 10. This graph continues on in this direction, and that's what that arrow means. So that concludes the lesson on graphing nonlinear equations using a table of values and plotting ordered pairs and all the other graphing equations. I hope you learned a lot, and I will see you in class.